I wanted to begin by welcoming and thanking you for taking the time to attend the Rennie Farm Community Health Meeting tonight. As many of you know, we have set up a community health advisory group, and Michael Swanwick, who's in the audience, will say a few words of introduction later. We decided to form this health advisory group to find out really what the main health concerns were of the community and how to best address them. After our first health advisory group meeting, for example, we decided to hold a community health-focused meeting that we're holding tonight and asked Dr. McClellan to present to us. A few other things that we're working on with the health advisory group is identifying independent health experts that would be able to consult one-on-one with the community and address specific health concerns. Developing FAQs, so we can start that tonight actually by listening to some of your questions and writing them down and having a health expert answer them. We're also identifying 1,4-dioxane in general specialists so that we can have another community forum presenting just on the science of 1,4-dioxane and remediation strategies. And of course, we're still working on the identification of past neighbors, that project that I talked about at the community meeting. And thank everybody who's suggested people contact me, and there's been a number. On a side note, I want to announce that we're still holding our drop-in hours, but not at Rennie Farm. It's a little too cold, a little too dark to be hanging out there. So we're going to be holding the next drop-in hours in our Environmental Health and Safety Conference Room, which is at 37 Dewey Field. I think it's this way, maybe. It's basically across the street in the parking lot. So we're going to have that in our conference room. And our next drop-in hours will be on November 17th from 3 to 5. And Dr. McClellan, Jim Week, and myself will be present to answer questions and discuss concerns about 1,4-dioxane and the Rennie Farm project. So I hope you're able to join us for this informal gathering on the 17th. I'd now like to invite Michael Swanwick to say a few words.
Hello, I'm Michael Swanwick. I'm a concerned neighbor like most of you are here. I am on the Health Advisory Committee that Dartmouth has organized to communicate some of the issues with the neighbors. We have also started with Marjorie's help over here, a neighborhood committee, the North Hanover Lyme Residents United Committee, which I am on the health part of that. So with both hats, trying to communicate well with neighbors' concerns, and then also communicate with Dartmouth to try to keep things open. So if any of you have health concerns as far as 1,4-dioxane, as far as the plan that GZA is doing, please, one of your avenues is to communicate with me. Marjorie has put out my email address to, I believe, everybody in the room. If you haven't seen it, please, can you... Marjorie's right there, plus Maureen has my email address. So I can act as a go-between to gather information and pass it through. I tried to collect some questions to bring before, to give Bob some extra time to answer those questions also. So that was kind of the start of that role of mine. So please be in touch. Thanks.
All right. Thank you, Michael. Okay, so we have a full agenda tonight, and the first person to present this evening will be Jim Week. He's our hydrogeology consultant from GZA. Jim is going to give a brief technical update on the Rennie Farm project. And before he speaks, I just wanted to ask the audience to hold questions until both of our presenters finish tonight. That way we can address, we can let Bob have his time and address the health-related questions because this is a health-focused meeting. But at the end of both presentations, Jim will go out to the lobby where there's lots of tables so he can unfold his maps and address your questions, your science questions. Please join me in welcoming Jim.
Thank you, Maureen. Can everyone hear me okay? I've got a mic on, just want to make sure. Is everyone okay? All right. So as Maureen mentioned, I wanted to give an update on the what we've been doing for the investigation out at Rennie Farm and kind of link that into some of what Bob's going to be talking about later on this evening. So we have our plan of the site, and this is the former burial area up here. And just so folks know, this yellow line running around here is the boundary of the Rennie Farm property. The red line is an area which is our preliminary groundwater management zone that's yet to be finalized, but that is the zone in which we believe we'll have groundwater with concentrations of 1,4-dioxane exceeding the groundwater quality standard of 3 micrograms per liter. So we're doing quite a bit of work. We have 56 monitoring wells that have been installed out at the site. Many of these are in locations where we have what we call a triplet well, where we have wells screened at different depths in the soil and also within the bedrock. And we also have another 18 monitoring wells that are currently under construction. Some of you folks may have heard our drill rigs down there. We have 3 drill rigs out working at this point to try and wrap these up as quickly as we can this month. In addition, we have 16 locations now that we're starting to collect surface water samples at. We did have 6 locations that's been expanded. Not all of them show on here. These yellow dots, this is in order to give you a scale that you could appreciate where the monitoring wells were. We sacrificed the ones that are out in the perimeter. We also have now passed the 100 water supply well mark for water supply well sampling. These white dots that show up are wells where we have sampled. I have another figure that you'll see a little bit later that will have a little bit better coverage, can show you where we have been. Within the source area, well, we can hardly see it here, a little spot here, we have done some additional work there. And if you saw one of the previous presentations, we had done a sampling of groundwater on a very intensive grid pattern and identified an area which we believe to be the source of the 1,4-dioxane. We went back into that area and we completed 70 borings, or 71 borings, I think, actually, within that area. And a lot of soil samples. I'll talk a little bit more about that on another slide, but that's been done. Geophysics, and then also we've sampled a number of ponds at the request of different folks and the reservoir for the town of Hanover. 1,4-dioxane has been detected at the locations that you see circled. Most of these are the monitoring wells in this area, but we do have, of note, the 9 Rennie Road property, which we've mentioned before. Also, more recently, the 668 Hanover Center Road property up here. And then you will see that out here, there's a surface water location where we have detected the 1,4-dioxane. What we believe is that there is being discharged in this area, as I'll show you in a moment, and it's flowing down the stream, and because of the low flow conditions that we currently have with the drought conditions, we're able to detect it, whereas in the past, monitoring in there, we did not see it. This area that's shaded in red there is generally the area where we have been detecting it in the groundwater. Again, the 668 is an anomaly at this point, and we're working to evaluate that. I'll talk more on another slide. What we like to do a lot of times is take a cross section. So this white line that I just threw on there is an area where, the next slide here, we've cut through the ground, and we're seeing up here the former burial area, the source area at the top of the hill. We also have the brook elevation down here at 850. That's right down this little notch here. And what we're showing, these little sticks are borings that have been completed out there, although one of these, this is a proposed boring. These wells over here are water supply wells. So this one being the one from 668 Hanover Center Road. The dashed line at the top is the ground surface, and this dashed line and the solid part here are the bedrock surface. Over in this area, we really don't have any data at this point. It's just based on the fact that we know it's fairly shallow up in this area, and the depth down here. And this is not reflected in this part of the cross-section, but at some locations we have about 90 feet of glacial till soils in the center of the valley, whereas in areas up here and over here, it's more like 10 feet or so. This well is the 9 Rennie Road well. And then what we believe is happening is this red line is representing the pathway that the contamination is taking, initially in the overburden or soils and shallow bedrock, and then diving deeper into the rock. And then as it hits the bottom of the valley, driven by the groundwater flow from the highland areas, similarly over here, represented by the red arrow, with the blue arrows over here indicating the directions we generally expect flow to be. Because of the flow going in this direction and this cap of low permeability soils, we developed very high pressures in the groundwater. And at this point, the elevation is 903 feet. Based on a measurement we have, we're taking more measurements down there in additional wells that we're putting in. But that puts it, if we look at this blue line that just came on, that's showing how high a column of water would rise. And so here would be at least 20 feet above the ground surface if you put a well down in here, which is actually what we had done to develop that. So over here is 668, and as most folks know, it's almost a mile away, and it's actually on the backside of the hill. The static water elevation, that is just, if it's not pumped, is about 990 feet, so it's about 40 feet down in the well. And it's sticking up out of the ground here because this cross-section doesn't go directly through it, so it's offset from the cross-section line. That's why some of these wells do not coincide with the ground surface, just to avoid confusion there. We did see, we've done some geophysical logging of the well, basically putting instruments down in the well to identify the locations of fractures, also to look for fractures that have flow coming from them. And then also sampling at the locations of fractures where there are flow and where there's flow, and also at locations where we just had fractures. In doing that work, we identified 4 zones where there were fractures in the well, but only one of those zones appeared to have a flow in it, and that was at elevation 940 feet. That's roughly 90 feet down into the well. And so we have samples out. We don't have the data back from those yet, but we hopefully will have those later on this week. Or beginning of next week, hopefully at the latest. Additionally, the interesting information, the pump is set at 790 feet, so there's about 60 feet of well beneath the pump, and the overall well is 300 feet deep. That's what we found. Previously in some of the drop-in sessions, we talked about well bore records that indicated around 305 feet, so it's pretty consistent with that. What we did find too is that the well yield is very low on that well. It's only 0.5 gallons to about a gallon a minute, and that's principally just coming out of that one fracture up here. So it really makes quite a puzzle hydrogeologically to understand how the 1,4-dioxane could be getting to that location. We do have some lab data that we're going to be getting in, and there's additional sampling that we may be able to perform to try and understand the source of the 1,4-dioxane at that point. But at this time, it's a very challenging model to imagine with this relatively low flow rate and largely water coming in at this relatively high elevation, which is above the elevation in the center of the valley, how it's getting there. But again, more work to be done, and we'll update you on that. One thing I did want to mention too is this one I just highlighted in yellow. As I mentioned, that one is a proposed location. That's more or less along the pathway that 1,4-dioxane would take going in this direction. So to look at the groundwater pressure in this area and the concentration of 1,4-dioxane will be very important as far as evaluating the potential for migration in this direction. And that's one of a couple of wells that are out in that area, but one that's closest to the cross-section line. Now, one of the other things I wanted to talk about, and this just kind of will segue into some of what Bob will be talking about, is just how are you going to be exposed, how could you be potentially exposed to 1,4-dioxane? And ingestion is really the way that we're most concerned about. The 3 microgram per liter standard is really assuming that's an ingestion of water. I've highlighted the 2 wells just as examples, and also the brook. If someone were drinking out of the brook, it's not really a source of water to drink out of. It wouldn't be appropriate for a water source, but that's a place that someone could encounter water. Also, dermal contact is another possibility. As I've mentioned, and I think Bob will probably have more to discuss on this, there's an EPA screening level of, I believe it's 230 micrograms per liter, as far as contact with the 1,4-dioxane. What we've seen in the brook so far of concentrations of no more than 0.5 micrograms per liter. But the brook, again, remaining highlighted because that is really the place where you could physically come in contact with it other than water from a well. The other one that really in the environment you're not going to see a possibility would be inhalation. And again, Bob can talk more about this, but showering or something like that. The number I mentioned, the 230, did assume actually showering was the activity that was causing the dermal contact. So I believe that it would include the inhalation. And I mentioned before that we have a figure showing the extent of the sampling. That's what this does. And we've highlighted the different properties to kind of better illustrate the coverage. The properties that are in blue are ones which are undeveloped, so there are no wells on those ones. Properties in green are all wells, locations where we have sampled the water supply well and we have data back indicating that there are no detections, no 1,4-dioxane present. The 2 red parcels, this is the 9 Rennie Road and the 668 Hanover Center Road. Again here, we're seeing concentrations around the 6 microgram per liter, and over here it was around 0.3 micrograms per liter. And then lastly, we do have some other lots here in more of a tan color. Those are ones where we've either just recently collected it and sampled back and don't have data, or we have scheduled sampling. I think at this point probably most of those have been sampled. And we are adding to this all the time. This map was updated last week, so we'll be updating this at least on at a minimum a bi-weekly basis and putting it on the website so people can keep an eye on the progress we make there. But at this point, we only have a few locations that are in here where we don't have some coverage, which is getting pretty good. So people's willingness to participate is helping out a lot here. This is the source area, and I just mentioned it because before I talked about the additional work there. Here was the area that I'd mentioned where we believe the source is located. Within that area, it was actually 71 soil borings. I updated it after I did my other slide. 139 samples were taken for 1,4-dioxane, 13 samples for radiological analysis, and then another 20 samples for a full VOC analysis using a method called 8260B, which has a long list of solvents, other compounds that would include any of the other things that we have detected at very low concentrations in the source area. One thing that we were asked to talk about today was just the treatment of groundwater and what these systems look like. We frequently use the term POE. That's referring to point of entry treatment system, and what that means is it's being treated from the point at which the water is entering into the home, so that all the water in the home gets treated. And it's really a pretty simple layout. Here's the well. We've got our flow coming up. We do put a flow meter in it so we can see how much water we pass through and keep a track of that so we know roughly when to anticipate what we call breakthrough of the contaminant. So the 1,4-dioxane and water are entering in here. We have an initial sample point here we call influent, which is going into the treatment system. We monitor that to understand what's coming out of the well. And then it splits, and this can be done 2 ways. You can have, as this has 2 parallel trains, or you can have a single train. In this case, we're representing 2 trains. So it's splitting and it goes into these canisters. There's a picture of them over here. They hold about 2 cubic feet of granular activated carbon. A lot of the times that's actually made from things like coconuts, things of that nature. But it passes through here, and really it's all about contact time with the carbon to get as much filtration as we can. So The more carbon you have, the more filtration you have, and less frequently you have to change these out. So it goes through the first pair and it comes back together, and there's a sample point here we call the midpoint. We collect samples there to see just how good these canisters are doing here, whether or not we have what we call breakthrough of those. So do we see any contaminant at this point? From there, it splits again, goes through the next pair, and then comes back together, and we have a final treated water sample here. For kind of an indication of how these work, the system at 9 Rennie Road has been in place for over a year now, and we've been sampling there monthly, all three of these points. Again, that concentration is generally around 6 micrograms per liter. We just now have seen breakthrough to the midpoint at a concentration below the standard, so we're scheduling the swap out of those canisters. What they'll do actually is to take these canisters in the front out, they'll remove the carbon, put new carbon in, those go into the back position, and the ones from the back go to the front. And that process is just repeated as necessary. But at this point, a 1 year frequency for change out on that system. Now the 668 location is going to be a little bit different because the concentration there is much lower. But I expect the change out would probably be less frequently than that. There are other potential treatment methods that can be used, but when you have a single contaminant, or just the 1,4-dioxane as opposed to a mixture of solvents and 1,4-dioxane, the granular activated carbon works fairly well, as we've seen from this location. And a lot of the other methods, there are flaws with a lot of them. I'm not really going to go into those now, but this is basically the technology that we're using. And that's it for my portion of the presentation. At this point, I'll turn it over to Bob.
Okay, our next speaker is Dr. Bob McClellan. Dr. McClellan is the chief of the section of Occupational and Environmental Medicine at Dartmouth-Hitchcock. For more information on Dr. McClellan's background, we have his bio on the back of the agenda. The title of Dr. McClellan's presentation today is 1,4-dioxane, What You Should Know. Please join me in welcoming Dr. McClellan.
Great. Well, thank you for coming out tonight, and I hope to make this interesting and something that you can apply to this specific situation and others that you confront in your life as we confront other situations where we're exposed to chemicals. So I got to get the other in a second. Where's the show? See it? Here we go. Okay, great. So we're on. So what am I going to do? I am going to begin with a course in toxicology. I'm going to try to explain some basic principles of how chemicals can cause harm to humans. We'll talk about how 1,4-dioxane could affect you or your children's health. We'll talk about this concept that you've probably heard a lot about of risk. What does that mean? How can we understand that personally? Talk a bit about the pros and cons of doing a health study of the community. Outline some steps that you can take to better understand and manage your risks. Listen and answer and hopefully address most of your questions. And at the end, I'll have some additional resources for you and your physician if you'd like to bring to them. At the very end of my presentation, and I think we're going to post this on the Dartmouth website, I also have some more technical stuff for those people who like to play with numbers. So what I'm not going to do is I'm not going to probably have answers to every question that you have. But we are going to capture them tonight, as Maureen said, so that we can get answers to you if they exist. Or you may have some questions that are really not my area of expertise. I'll refer them to Jim. He may be able to answer them or otherwise find the right resource to answer those questions. And in some cases, unfortunately, and this is one of the challenging aspects, there really are no clear answers to some of the questions that we all have. I'm also not here tonight to provide personal medical advice. This really is not the right venue to do that, but as Maureen mentioned, we are going to make that available in another setting. So, how and whether a chemical causes harm depends on a number of things. First of all, its toxicity. How harmful is it? How toxic is it? Its cancer potency, its chemical and physical properties, the dose that you're exposed to, and you as an individual and how susceptible you are, because we're all different. I'm going to explore each one of these things so that hopefully by the time you leave tonight, you really understand each of these points. But before I do that, just take a giant step backwards and say, so how do we really know anything about how chemicals can harm human beings? Well, the best way we have of understanding that is actually studying people who have been exposed to a chemical, particularly in large groups of people. It's called epidemiology, looking at the types of health effects that occur on exposure to a particular chemical. We know about some chemicals that way, but there are a great many more that we don't have that kind of information that gives us that detail. So then we depend upon animal toxicology. These are experiments that are done in a laboratory under controlled conditions where animals are exposed to different doses of a chemical. The other tool that we can use are lab experiments that occur not in an animal, but actually on a lab bench. It can be in dishes, in test tubes, et cetera, where we can look at how a chemical affects a cell, and how it may affect a gene. And then finally, we can oftentimes predict pretty well how a chemical might harm an animal or a human being based on its similarity to other chemicals. So what do we know about 1,4-dioxane from a human perspective? So we do have information from human beings around inhalation in an occupational setting at very high levels, at short-term exposure and over a long term. We also have some information about the relationship between exposure of human beings and cancer. And we have some information about short-term exposure to the skin in human beings. We have much more information from animals, where you can see most of these blocks are filled in, both in terms of different time frames of exposure, but also in terms of different organ systems that can be affected. So it turns out that chemicals differ in toxicity. And toxicity means the capacity to cause harm at a specific dose. It turns out that, in fact, every chemical is toxic. What matters is how toxic it is. Water is toxic, but not very toxic at all. If you drink too much, you will actually have a seizure. You could even die. But that's a whole lot of water. That's very different than this pesticide, which you can buy in your local hardware store to kill various pests. This malathion is extremely toxic, and you take a very small amount of it, and it could kill you. So that's the difference in the toxicity. They're both toxic, but what matters here is this, a very small dose could cause harm. Here, it takes a very large dose to cause harm. Now, just as chemicals are different in toxicity, we also use a term carcinogenicity, the ability of a chemical to cause cancer. And just as with toxicity, chemicals differ in terms of how toxic they are, that is true also with cancer. And we generally talk about how potent a carcinogen, a cancer-causing chemical, it might be. How do we know how potent a cancer is? Well, we use evidence similarly to how we understand toxicity, and it's called the weight of the evidence. How much evidence do we have, and how much certainty we have that a particular chemical causes cancer in human beings. So we look at many different, we look at chemical structure, we look at genotoxicity, we look at animal carcinogenicity, and then best evidence is, of course, human evidence. And it turns out that organizations such as the Institute that studies that conducts research on cancer has a way of grading how strong the evidence is. There are different types of classifications. The EPA has different letters and numbers, but they're all basically the same. And this means that at the very top is where we have so much information from human beings that we can say it's a definite human carcinogen. A definite human carcinogen like cigarette smoke or like radiation. We know we have so much information about that. There's, at the very bottom, it's classified as a chemical that we have so much information about that it's not carcinogenic that we can say it doesn't cause cancer. And then in between, we have varying amounts of information. Once we get up into this area, we have a lot, and we have sufficient animal information. We say that it is probably or likely to be a human carcinogen. That's different than saying a definite human carcinogen. We're saying it's probable because we know it causes cancer in animals, and we have a lot of human evidence, and there's some similarities. But we're not certain because we don't have evidence in human beings themselves. So the second concept here is around potency. So just like chemicals can be variously toxic, so carcinogens can be variously potent. And so it turns out that here dioxin, which is not the same thing as 1,4-dioxane, they're different chemicals. This chemical, a very, very tiny amount, will cause cancer. It takes much more for 1,4-dioxane to cause cancer. And so there's a whole list, and you can look up on a list and see the various potency of different types of carcinogens. So, what do we know about 1,4-dioxane? We know in human beings that it has caused death. These are human beings who have been exposed at extremely high levels in occupational settings. These people have had organ damage. We also know in human beings that there is such a thing as a safe threshold, meaning a level below which no harm occurs. And we're going to go into that in more detail. We also know, according to that previous scale, that it is a likely human carcinogen. And we say that because of the animal information that we have that we'll talk about. With a carcinogen, we assume there is no such thing as a safe level, and we'll talk more about that. What we don't know from either animals or human beings is around reproductive and developmental effects in the womb. We don't have enough information to come to any reasonable conclusion about that. So, very high dose exposures. This would occur in an occupational setting. We have human evidence, and as I mentioned, death, critical organ dysfunction or damage occurs liver, kidney, and in the upper airways and in the lungs. We have, in terms of longer-term dose exposures, very limited human evidence. But we do have evidence with respect to animals. And we know that given a certain level of exposure over a long period of time, we can cause damage to the liver, the kidney, and the nose of rodents. What do we know about reproductive and developmental effects? Well, unfortunately, the amount of evidence that we have in human beings is extremely limited. There is some information about there, but not with exposure to a pure 1,4-dioxane. Instead, and this would be common in an industrial setting, there were a group of pregnant women who were exposed to mixed solvents in which there was 1,4-dioxane was a was present, but there were also many other solvents. And we already know right now from plenty of human evidence that there's a number of solvents that can cause human reproductive effects. We have very limited animal information that has been published. Doesn't seem to be a significant effect at the inhalational level. No conclusive effects on the oral ingestion, although there's a couple of studies that do look at very high levels showing lower weight offspring and some minor bone problems. What do we know about potential cancer effects? Well, again, very limited human evidence. That evidence that we do have, several hundreds of workers, has shown no evidence that it causes cancer in humans. However, in animals, it is a definite animal carcinogen and has caused cancer in liver, kidney, and nose. That's what makes it a probable but not a definite human carcinogen. So, what's the same one? Same one. So let me get back to the grandfather of toxicology, a guy by the name of Paracelsus. He lived a long time ago. He was a smart guy. And he was the guy, he's thought of as the grandfather of toxicology. And this is his famous quote. In other words, the dose makes the poison. What I've just told you about is that 1,4-dioxane can be harmful to human beings. Now what I'm going to tell you is it all matters on the dose. That's what matters, is the dose. It matters how toxic it is. It matters how potent it is as a carcinogen, because that affects how much of a dose is going to be harmful. But now we need to know how a dose impacts whether or not you're going to be harmed. So let's start out with a common understanding of dose. Pills. We know we can take a couple of pills and it will be a safe dose. We know if we take the whole bottle of pills, it can hurt you and even kill you. We also know that if the pills stay in the bottle, you're not exposed to it, you have no dose, and it has no way that it's going to hurt you. You have to be exposed to that pill to have either a therapeutic effect or a toxic effect. So let's turn this to a chemical that we're also all familiar with, alcohol. Over here, you take a dropper. You take 1 drop of alcohol. Over here, you ingest the entire bottle of alcohol. This could kill you. This you probably won't even notice. So let's talk about now 1,4-dioxane in water, because now we got to begin to think about this concept of concentration and how it impacts dose. So with a pill, there's a certain concentration that's like milligrams, like you take a certain number of milligrams, that's the concentration. So we also need to think about concentration of chemicals. So it turns out that 1,4-dioxane in drinking water is measured in micrograms per liter. Now a microgram is a very small weight. Most of the pills that we take are in the milligram size. If we take salt, 2 grams, 2 to 4 grams in a day. A milligram is 1,000th, a microgram is 1,000,000th. And just to try to get some sense of what that means, it turns out there's 60 billion drops of water in an Olympic pool. We measure micrograms per liter is also equivalent to parts per billion. So 1 microgram of dioxane is like 1 drop in an Olympic swimming pool, which has 60 billion drops in it. So the levels that we've detected, I think as we know, and one of them is off the screen here, but is in the 6 microgram per liter and the 0.3 microgram per liter. So the next thing we need to know as we understand how a chemical could potentially cause harm is about its chemical and physical properties. So if I take this plastic, right, and try to get it in my body, well, I have a hole, it might go in. right? But it's not going to go in. The physical property of this as a solid is not going to go into me. If I take this water and pour it on my skin, it actually doesn't go in very well because of the way my skin is generated. But if I go like this, that is going to be well absorbed, okay? So the different properties, the chemical and physical properties are going to impact how it gets into the body, where it goes in my body. Does it go to my brain? Does it go to my bone? Go to my liver? How it's processed, and then how it leaves my body. So let's talk about 1,4-dioxane from that perspective. So here's a human being, and here's the 1,4-dioxane over here. This human being, no problem if the 1,4-dioxane stays over here in the barrels, right? The concern is if the 1,4-dioxane comes out of the barrels, where does it go? That's Jim's job. He figures out when it's released into the environment, where does it go? Well, we know it goes into the soil, but then it goes into the water, right? So here are the 4 different areas that it could go into: the air, the water, the soil, the food. We could then inhale it. If it's in the air, maybe a little bit aerosolization in the water. It could contact our skin. We can ingest it. Or if you're pregnant, it could potentially, the question is, could it go across the placenta? And what about if you're breastfeeding? So water is the area of concern because we know, first of all, that's where it is. Secondly, if you ingest it, there's virtually 100% absorption. What about if you inhale, as workers do? Workers can inhale 1,4-dioxane, and about 80% of that is absorbed. Very, very, very little of it, however, is absorbed through the skin. So understanding the chemical and physical properties of dioxane is helpful. We know that it's metabolized very quickly. It goes out of the body within a day or two. Okay, it's very water soluble. And it turns out our body processes it very efficiently. So theoretically, you could measure it in the urine. However, it goes through so quickly that you'd have to measure it on the day of exposure. And it turns out at the types of environmental exposures versus occupational exposures, which are much higher, it's very unlikely you would detect it. So the other thing that we need to think about is that there are actually many sources of 1,4-dioxane. So certainly we're here tonight because we're concerned about a waste site where 1,4-dioxane has breached the barrels and is getting into the environment. But it turns out that 1,4-dioxane is actually fairly prevalent in the environment. We're going to talk about some of the areas that it is. So when we think about exposure, okay, if I'm drinking out of this, that's one source of exposure. If I go over to this chair over here and pick up another glass, same water, and I drink it, I'm getting another exposure. If I come over here, pick up another glass, I drink again. The point is, the total exposure is actually what matters, right? It's not just this, but I'm also concerned about these other sources of exposure because they all contribute to dose. So this is meant to point out that our environment is full of chemicals, and they can contaminate food, our indoor air, our house dust, and products that we put on our skin. And that, in fact, there have been studies done by the federal government as far north as the North Pole, as far south as Antarctica. And in today's day, we now can find chemicals in penguins. Where are they? They're in the south, I guess, and polar bears. So this is not just where we live in kind of populated areas, but now kind of human beings have contaminated our environment with many, many low levels of chemicals. So what about 1,4-dioxane? There are many consumer products that have historically been contaminated, not on purpose, but trace contaminants with 1,4-dioxane. A variety of personal care and household products, and some food containers, wrapping, pharmaceuticals, various adhesives, paint strippers, grease, plastics like PVC. So 1,4-dioxane has actually been in our environment in a general way in many of these products that you use. And if you go online, for example, here, you can look up products that have 1,4-dioxane in it. These are just some of the common consumer products at trace levels. There has been some FDA action around this, trying to limit the amount of in the food containers, for example. Many manufacturers have been voluntarily reducing it. So today our exposure to 1,4-dioxane in consumer products is much lower than it was several years ago. So our dose now depends upon concentration, right? And the route of exposure, how much we absorb of it, and also the duration of exposure. Is it a brief exposure, short term, or is it a chronic exposure over the long term? And one of the important things to understand about the way that toxic chemicals can work at high dose or versus long term, and especially with cancer, is cancer has there's this concept of a latent period. A latent period means that if you get exposed to something that is a definite human carcinogen today, you're not going to get cancer tomorrow. It takes a period of time for the cancer to evolve. It's a little bit different with different types of products. With asbestos causing mesothelioma, may take it as long as 40 years before the cancer actually manifests itself. Other chemicals, it might be in the 15 to 20 year period of time. So now what I want to do is to start thinking about how dose actually results in a particular effect. So the response of the body to a chemical is directly dependent on the dose. What we've talked about now is associated with the concentration, the exposure, is it short term, and through what route, and how long you're exposed to it. We talked about how all chemicals are toxic at a sufficient dose, depending upon how toxic the substance is, that most chemicals are not toxic below a safety threshold. And we've also talked about this concept, we've begun to talk about, I'm going to talk more about it, that carcinogens, we're assuming, have no threshold. But still, even though we're assuming that there's no safe threshold for a carcinogen, the dose still matters. The lower the dose, the lower the risk. If you smoke one cigarette in your whole lifetime, it's very different than smoking 3 packs a day for a whole lifetime. So that's how dose matters. So, from a toxicity perspective, again going back to our dropper of alcohol versus a whole bottle, we understand that there's a level, a threshold below which no one, not even a fetus, is going to be harmed. That's a concept of a safe threshold, which is going to be important when we then talk about some of the levels that various state and federal agencies have put out. Now, the other thing we need to be thinking about, in addition, is this concept that all of us are different. We're different sexes, we're different ages, some of us have various health problems, we have different lifestyles, our genetic makeup is different, and because of that, we all have different susceptibilities. So if we took a room of people and all exposed them to the same thing, we may have very different impact on different people depending upon who you are. So the likelihood or risk of harm depends upon how toxic the substance is that you're exposed to, what your exposure is like to that, how much of it, over what period of time, and your individual susceptibility. Harm is not going to occur if you're not exposed to it. The likelihood or the risk of harm will increase as the harmfulness, or the toxicity or carcinogenicity of the substance increases, or the dose increases, or your susceptibility increases. So, what about 1,4-dioxane and environmental safety threshold levels? These levels are meant to be established to be protective of harm to the most susceptible individuals, including children and fetuses. Now, I've already told you we don't know about children and fetuses, but there are ways that we put in additional safety factors that are meant to, presumably, as best as we know, protect even the most susceptible individuals. So that's where we set these protection levels much lower than those that have been shown to cause harm. So the Agency for Toxic Substances and Diseases Registry, ATSDR, took me 4 years in medical school to learn how to say that, sets what are known as minimal risk levels, or MRLs. And these are meant to be safety thresholds for non-cancer effects based on the best evidence that we have for the most sensitive effect for a specific exposure duration. So, for example, we know inhalation of dioxin can cause nasal irritation, it can cause kidney, it can cause liver. They figure out what's the most sensitive part of a human body or of an animal that actually is harmed, and then they set that level based on that, but it put in uncertainty factors to make it more protective, and I'll talk more about that in a moment. These factors generally, and I guess I'm going to talk about it right now, these factors get at this issue that people are not animals, most of them anyway. And so we say that if an exposure causes what's the lowest exposure that causes any harm in an animal, and then we're going to try to interpret what is that like in a human being, we're going to lower it by tenfold. We're going to lower it by tenfold in general. We also then recognize that people are different, and we're going to lower it by another tenfold. So in other words, we find a level in an animal, and we're going to lower it by 100-fold. Now I'm just giving you an example. Depending upon the chemical, this is done somewhat differently. So what about 1,4-dioxane and this notion of an MRL, or minimum risk level, a level below which we don't anticipate any harm to susceptible individuals? Based on liver damage in rats, they set a level 100 times lower than the rat harmful dose at 100 micrograms per kilogram per day. Now that doesn't mean 100 micrograms per liter, that's 100 micrograms per kilogram per day, which means that the average person drinks 2 liters of water a day. The average adult man weighs 70 kilograms, 155 pounds or so. They would not be anticipated to be harmed unless they drank more than 3,500 micrograms per liter. So that's how you think through what this would mean. Now, what about acute exposure? Well, acute exposure is shorter time, not as much exposure. Not surprisingly, 5,000 micrograms, meaning you could take more than if you were exposed day in, day out over more than a year. So that's set at 5,000 micrograms per kilogram per day. So it turns out that because we know we can be exposed also by inhalation, they set up, and this exposure route and the way we absorb it, the way is different. The ATSDR sets up different MRLs for the inhalation route. And here they set it at 0.03 parts per million based on causing sores in the noses of rats, and they set it 300 times lower than a harmful rat dose. And for short term, you can see it's a little bit higher. Again, this is based on human data, experimental data, where they had human beings in a chamber and they exposed them, and they looked to see what happened, and they found over a short period of time that humans started to complain of nasal irritation at about 20 parts per million. So they set it 10 times lower than that because we're actually working with human beings. So there are many other groups that kind of weigh in here in terms of this concept of a safety threshold. The EPA does its work, and it does work around something called an oral reference dose. Now this means this is a dose you could take not just for a year, but for an entire lifetime, for 70 years, and we would anticipate no harm to the most susceptible person in a population. And here they set it at 30 micrograms per kilogram per day. So then you can do the math if you wanted to in terms of 2 liters a day, 70 kilogram man, et cetera. And they base this on the rat liver and kidney toxicity. They also establish a similar number for inhalation at this level, 30 micrograms in air. So I'm going to summarize this part of what I've talked about with respect to the likelihood of toxicity, meaning non-cancer effects from environmental exposures at Rennie Farm, or for that matter, anywhere in our environment, is extremely low based on our current science and the measured levels of contamination. What about cancer risk? If I'm exposed to a carcinogen, won't I get cancer? If I'm exposed to a carcinogen, won't I get cancer? So we're going to now start talking about carcinogens, and some of what we have already talked about in terms of toxicants is going to be the same, meaning if you're not exposed, you're not going to get it. The more you're exposed, the higher the risk. We need to talk about this concept of risk because it's a complicated, kind of hard thing to get your head around. And so as I was trying to think about how to talk to you about it, I said, well, let's talk about cards, because most of us has played cards at one point or another. And some of you may have played cards and said one-eyed jacks, of which there are only 2 in a deck of 52, are wild, so you can make it anything you want. There are 2, and I lost anyway, that said 2 out of 52. So in other words, if you started pulling cards from a deck, your chance, or your risk, if it was bad if you got a one-eyed jack, would be 2 out of 52, right? Or 1 in 26. However, if what you were trying to do is to just pull one more heart so you could make a flush, right, in your poker hand, you have, 13 hearts. So it's 1 in 4 chance, right? So here it's 2 in 52, here it's 1 in 4. Different chance or different risk. So let's think about now the extra chance, the extra risk of adding one more one-eyed jack to the deck. I take it from underneath the table and I put it in my hand, right? So if you added 1 jack to a deck of 52, so it has now 53, you'd have 3 out of 53 chances. If you added 1 one-eyed jack to 1,000,000 decks of cards, you would have 1 more chance or an excess risk of pulling a jack. In other words, 1 in 1,000,000. You'd only have 1 in 1,000,000, right? Over here, you put 1 in a deck of 52. You now have 1 extra chance. And the reason why this is important is because we're going to be talking about risk of cancer as an excess risk. The deck already has 2 one-eyed jacks, right? Turns out there are already people in the community who get cancer. The deck has 2. If we put in 1 more, that's an excess chance of a one-eyed jack, right? If we put 1 more jack in 1,000,000 decks of cards, just 1 jack in 1,000,000 decks of cards, otherwise they all have their 2, right? And now you start pulling, you have 1 excess chance of getting a one-eyed jack when you pull it. So let's talk about cancer risk now. Hopefully you understand this concept of risk. When we talk about risk of cancer, we assume, unlike the risk of a toxic effect, we assume that no matter how low the dose is, there is a potential risk of cancer. We know, because we've talked about cancer potency, that one chemical may be less potent and less likely. In other words, you have to go way out here to get a similar risk. And here you get get there much faster, gets to this risk because it's more potent. But in either case, the higher the dose, the greater the risk. The higher the dose, the greater the risk. The corollary, of course, is the lower the risk, the lower the lower the dose, the lower the risk. So, how do we know about cancer risk? I've already told you, with most chemicals, we actually, for this particular issue, we do not have good human data. We just don't. So we depend a lot on animal exposures. And we depend upon exposing animals at high levels, because you can't have thousands of rats exposed at various levels, at low levels. So the way this curve works is we assume that if we expose the rodents at this level, and a certain number of them get cancer, as we go down, we draw a straight line, a slope, based on what we understand is how potent that chemical is. And we estimate what the human exposure will be down at the kind of levels that we're exposed to in the environment. So this is a mathematical calculation. It's not known for sure. This is based on models, actually, in terms of understanding how radiation works, which is one of the first human carcinogens that we've really understood. And we know that radiation works like this, at least pretty close down to the zero. There's some people who think it may be a little different down here, but pretty much. So this is a conservative estimate. It turns out it may not go down to zero. It may stop. There may be a threshold, particularly for chemicals that are not genotoxic, meaning they do not have the same mechanism of causing cancer that radiation does, which means harming a gene. Turns out 1,4-dioxane, fortunately, is not genotoxic. And so there is some people who feel that there may be such thing as a safe threshold, but we don't know. So we assume there is no such thing as a safe threshold. So these are the cancer risk estimates that are the most current that the EPA publishes. And they are estimating, based on the kind of mathematics we just talked about, that an exposure at about 0.35 micrograms per liter, drinking 2 liters of water a day for 70 years, exposed that whole length of time, will have one excess cancer in 1 million people. That's one extra one-eyed jack in a million decks of cards. Okay? So that's how to understand that. Higher levels, higher doses, higher excess risk is the way to understand that. At the very end of my presentation, as I mentioned before, I have lots of formulas. If anyone wants to play with this, you're welcome to. So I know one of the questions has been around this concept of exposure to 1,4-dioxane while showering. And Jim talked a little bit about this. And what is the risk? Why is it said you can shower but you can't drink with water? Well, it all gets to this issue of the chemical properties, the physical properties, the absorption, the routes of exposure. And it turns out that people have done kind of the math and figured that if you took a shower that lasted 33 to 45 minutes, hopefully not in the current drought that we have, and you stayed in that bathroom for a total of 60 minutes, that if the contaminant level would have to be 24 micrograms per liter, and you have to be exposed for 30 years to have one excess risk of cancer in a million. Another way of thinking about this, in terms of the total risk associated with having a well water that you drink and shower with, is that 97% of the risk is associated with drinking and a very small amount associated with showering. So the timing, I think we already talked about timing of harmful effects. So you can have an acute exposure, a chronic exposure. You can have an acute effect, means it happens very soon. That would happen only with very high dose. Or The issue really with cancer is delayed and this concept of latency that we talked about. So what is your risk then of illness related to 1,4-dioxane? No exposure, no risk. Based on what we have measured in the wells in the area now, on the detected levels, there's negligible or no risk of toxicity associated with 1,4-dioxane. And that is true essentially with any environmental exposure, because it's all at these low levels. What about children and toxic effects? I've told you we really don't know with children. Children are oftentimes more susceptible, sometimes less susceptible. But these levels that we've talked about are very conservative, have these fudge factors put in to try to take that into account. What about breastfeeding? It turns out that one of the properties which has been so challenging from containing the contaminant is that it's very miscible or kind of dissolved in water, so it moves very quickly. That's a good thing from a breastfeeding perspective, which has a lot of fat in it. There's little transmission in breastfeeding. What about the risk of reproductive and developmental effects? We don't have enough evidence really to say one way or the other, although there is such a thing in this world. This is a toxicity issue of safety thresholds with respect to reproductive and developmental effects. We just don't know what that threshold might be in human beings. What about treatment for 1,4-dioxane if you are exposed? The treatment is remove from exposure. There is no antidote. You don't take something, you don't take vitamins, you don't take any pharmaceutical agents, etc. So then, this issue of will you or your child have a future health problem related to 1,4-dioxane? What is your risk? No exposure, no risk. An exposure, no matter at what level, does not mean you will have a health problem. It really relates more to this concept of risk that we've talked about, or possibility, which is related to your dose, your susceptibility, other types of exposures you may have, your lifestyle. Now, one of the things that's challenging, of course, in trying to sort out whether or not 1,4-dioxane causes problems is we all have health problems. As we go through our lives, we all have various health problems with our kidneys, with our livers, with our nose. We will have these problems and we will have cancers, whether or not you're ever exposed to 1,4-dioxane. Just to kind of try to understand, put your head around this, the issue of cancer, 40% of us will be diagnosed with cancer at some point in our lifetime. It's just a current fact of our lives. And it turns out that I'm sure everyone in this room knows people with cancer. And if you know people with cancer, you probably know people who have had different types of cancer, just like people have different types of infections. And just like different types of infections are caused by different types of bugs, and you may get pneumonia or may get meningitis or you may get infection of a wound, different chemicals can cause different cancers. So you don't say a chemical causes all cancer, you say a chemical causes certain types of cancer. And with respect to 1,4-dioxane, we were saying that it causes, so far as we know from rodents, it would cause liver and kidney cancer. So, what do we know about liver and kidney cancer? It turns out that 39 people every year, or per million people, are diagnosed as having kidney cancer. Over a lifetime, in 1 million people, 17,000 of those will develop a kidney cancer. If we had one excess cancer in 1 million people, we would then have 17,001 kidney cancers. If we think about this from a liver perspective, we get 82 new diagnoses a year per million people. Over a lifetime, 9,000 per million. If we had one excess case due to a chemical exposure, we would then, in that population, have 9,001. I've talked about toxicity. I've talked about cancer. But now I want to talk about another very real problem, It's called stress, worry, uncertainty. These kind of events in a community cause this, and it's not pleasant. The notification that you're living in a community near a hazardous waste site, with all of the uncertainties associated with that, and how it evolves over time, drives a lot of people crazy. I mean, it's very difficult and very challenging. I'm hoping that what I've been able to do tonight is not certainly to answer all these questions. I'm going to talk more now about what you can do. To tell you what we know, what we don't know about how toxicology works, what we know about 1,4-dioxane. I hope that some of that, anyway, will help you with some of the stress and worry associated with the health issues associated with this chemical. But it's clearly understandable why people are worried. One of the most important things, I think, in addition to understanding toxicology, is it's nice to be able to do something. It's nice to be able to do something when you feel like you're being threatened in some way. So one thing you can do is to keep up to date. This is an evolving story. Stuff is posted on the Dartmouth site on a regular basis, communicated in meetings, in other ways. You've got some community-based advisory groups to bring information back and forth. Certainly either address your concerns and questions to them, and they can bring them to us, can bring them directly to Maureen. It's also useful if you're thinking about your health and how it relates to the chemicals in our environment, to learn as much as you can about how to reduce your exposure to hazardous environmental chemicals and agents. Because what's ultimately going to matter from a health perspective is what are you exposed to, not just from the Rennie Farm site, which is important to understand, but also other exposures that you may have. I'm going to provide you some resources that you can learn more about that. There's no special health examination for exposure to 1,4-dioxane at the kind of environmental levels we're talking about. But routine health maintenance exams are there to try to detect and screen for cancers in a way that so that they can be treated early on. Living a healthy lifestyle. Talk to your PCP. If you're worried, your PCP may not have a level of comfort in explaining this. They may help you with some of your anxiety and worry. It is okay to give your PCP my name and number, which will be published, and I'll be happy to answer any questions your PCP may have to help work with you. Now, I wanted to turn now to some questions that I've heard that have come from the community. So one of the things that's come up is, well, why don't we do a community health study? Then wouldn't we actually know more about what's going on? Well, there are problems with this, and I think probably you can begin to understand some of the problems we might have in doing such a study. First of all, the number of the people in the community is very small. The numbers that I was showing were kind of millions of people to be able to detect even one extra cancer. Some of the people from the community are no longer here, and we might never be able to get in touch with. Also, some of the symptoms, meaning kidney problems, liver problems, and cancer, even in those, are relatively common. Only a handful of people now have any known exposure to 1,4-dioxane. Not millions of people, a handful of people. And then the other thing is that this is not the only site of exposure. So over your lifetime, you've been exposed to 1,4-dioxane through other products, as we've talked about, and thousands of other chemicals, some of which are carcinogenic. If you've ever been to California, and you know they have a law there that wherever there may be a carcinogen, they have to post it. Any public building that you walk into there has a sign, a warning sign. This environment you're about to get into has carcinogens in it. I don't think that's very helpful information. But the point is there's a lot of this stuff around. Minimizing this is a good thing, and so knowing how to do that is a good thing. And then the current likelihood, so far as we know, of a handful of people being exposed at extremely low levels, and what we know about the kind of risk, is the likelihood that we would detect anything is extremely, extremely remote, and it would be very hard to know whether it was related or not. Some of the other obstacles get a little complicated, but let's say we just looked at everyone right now. Well, then we're going to miss people who, let's assume that the exposure for a moment just started, say in the last year, 2 years, I don't know. Remember the latency period? If we studied today, we're not going to detect it. You'd have to go out for 15 years. So a cross-sectional, studying everyone today wouldn't help. What about looking backward? Well, people who have that cancer that may occur because exposure didn't start until recently wouldn't be counted in a study looking backwards. We also don't have any measures. We have no idea what people were exposed to, if at all, in the past. What about a prospective study? What if we started studying today, everyone in the environment, and looked forward? Well, we'd have to wait at least 15 years before we had our answer. And any study that we did couldn't be just a question, do you have cancer or not? It would have to be much more complicated than that. We'd need to collect a great deal of information, death certificates, medical records, laboratory tests, et cetera, et cetera. And experience at very serious hazardous waste sites like 3 Mile Island or Toms River in New Jersey with unbelievable exposures over a long period of time continues to this day to be frustrating in terms of actually being able, using human epidemiology, to draw these kind of conclusions. So now just a couple of other questions. And this was a question around with the detection limit recently lowered from 3 micrograms to 0.25 micrograms with some of the new technology that's available. Is it likely that the EPA or state will lower the allowable drinkable drinking water limit? And so there's a few different things not to mix up here. I've shown you some numbers which relate to cancer risk, 1 in a million, like 0.35, 1 in a million excess risk of cancer. That's not the same thing necessarily as a standard. So the EPA does not have a drinking water standard that it insists that your community supplies of water meets. They're thinking about it, and they're asking community suppliers to start measuring it to find how much is in community water supplies, but there's not a standard. At the state level, many states have levels. And the level in New Hampshire currently set at 3. I'm not the state. I don't know if they're going to decrease it. They may. Other states have recently. Massachusetts is at 0.3. Colorado is at 0.3. Michael said California went down. It had been 1, but I guess it's down to 0.4, is according to Michael. So different states currently have different levels to trigger mitigation. Many states don't simply adopt the EPA risk estimates. Some do their own. They also have to address issues of how many wells may be contaminated, because this chemical has been relatively ubiquitous. So if you keep pushing it down low enough, you're going to find it in many, 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 many more places. So there's a lot of complexity to trying to figure this out, and I don't know what New Hampshire's going to do. Someone asked a question around relationship between 1,4-dioxane and acoustic neuromas or vestibular schwannomas, type of cancer that occurs in the ear as it may relate to 1,4-dioxane. I couldn't find anything in the literature around that. There are genetic risk factors. There are diseases that put you at risk of this particular type of ear cancer. And there are some, in fact, environmental risk factors, such as childhood exposure to low-dose radiation. You've probably seen varying kind of reports in the newspaper around cell phone use and whether it did or didn't cause brain cancer. There's a lot of conflicting data. And similarly, also some concerns with conflicting data whether noise might. There's no association with these cancers with solvents or 1,4-dioxane that I could find. So with that, I'm going to stop. I've gone on for a long time. And you may all want to just split, or you may want to ask a question. And I will have a bunch of resources that are at the end of this that you can access if you want to. Yes, sir. I think they want you to use a microphone. So if you could just hold it for a second. Maureen, this gentleman here. Huh?
So based on what is known about the Rennie Farm contamination, is it possible, and I understand this is difficult, is it possible to state it can never go so far? Like the limit is 3 miles. It can never go further than that. And I'm just picking that number out. Is that something that could be stated?
Right. Well, that's a Jim question.
That's okay. That's
Yeah. Yeah.
Okay. Maybe may I ask my other question?
Yes.
That perhaps relates, it builds on your experience and all the knowledge you have. It's not directly related, but it certainly builds on it, and perhaps you could provide some advice. The health concern is number one, of course, but our group is also very concerned about the effect of the perception or the reality of the contamination on the property values and sellability of the homes. And to bring some reality to that, perhaps you know, at least 2 buyers of homes in the area around Rennie Farm have withdrawn their offers. So it's going to be hard to sell homes, and the property values are decreasing, at least the perception of them. So, and I could ask this question in many different ways and qualify it, but I'll try to keep it as open as possible. And you could maybe respond better then, or in a more effective way. What would you recommend for us or Dartmouth or whomever to do to reduce the perception, which could be real or misperceived, the excessive concern that might build up in the market, the buyer market, for our properties? What would you say? You made that very kind of summary. It's a very low chance of having a problem on one of your slides. But how would you go about forming that statement or presenting it to those out there who might want, who could be potential buyers? We bought our homes there because it was a very nice area to live, and it still is in all the ways except for this concern. So the question is, how might we reduce this perception, misperceived or real perception, which is a combination of both probably, about our property values and sellability?
Okay. Well, I am going to answer that in a very narrow way.
Sure.
Because I certainly am not a realtor. My mom was.
Right.
But it didn't wear off on me. And so I really am not an expert in terms of property value or anything else like that. But I think what I can answer is something very important. And actually, one of the things I hope to try to address tonight. And that is that we all perceive risk in our lives. We perceive it differently based on our background, our knowledge, how closely it, if it's him, it may not seem as risky if it's you, right? There are a lot of factors that go into this concept of how we perceive risk.
Right.
What I've tried to do tonight is to provide you some science, some knowledge that could impact how you perceive your risk. But if you looked in this room and we asked everyone in this room, even after tonight, probably we'd have different levels of perceived risk based on a lot of factors.
Sure.
I feel, as what I do, communicating about risk, one of the things is for people to have accurate, pretty scientific assessment of what risk really is from a health perspective. Now, that's not I can't answer the question around property risk per se, and I understand the question that you have. And I think that there's some, do you have an open,
About our real estate.
yeah.
I think you know that we have a real estate group that's separate from our health advisory group that is looking and meeting with folks one-on-one right now and determining the issues. And they're working on making a recommendation to our upper administrators at Dartmouth College. They may have an open community forum to discuss, but they're encouraging you, if you do have real estate concerns and issues, to contact the director of real estate at Dartmouth College. And we have a sheet outside, because we thought we might get this through an email to set up an appointment. Okay. And I think Jim has you have a question for
There is a
Jim.
question for,
Well, if you still want to take that question. I don't want to hog all the question time either. So, the question I had that was referred to you, Jim, was based upon all we know regarding the Rennie Farm contamination, can it be stated it will never go beyond 3 miles or 5 miles or whatever? Is it possible to do that?
Not at this point. I think at some point, we might feel more comfortable with that. But right now, what I showed on the slide before, we have 56 or so wells installed, but we still have some more that we want to put in. One thing that didn't go into a lot of detail.
oh, he wants you on a mic. She wants you on a mic.
I'm sorry.
So I turned it off.
Oh, okay.
Turned it back on.
Do you want to just
So I didn't get into a lot of detail because that really wasn't the focus of the talk, but what we do have now are a number of wells to the north of where we've detected it in the past, off-site, which have been clean. We haven't detected it in those. Those are primarily in soil. We are in the process of putting in wells in bedrock in that area, and that will help us better answer that question. Similarly, on the other side of the stream there, I mentioned a couple locations that we're going to put in wells. Those will kind of have the same effect there of trying to delineate it. Because of the bedrock structure, we think it moves towards the northeast, and all the evidence points to that being correct. And that structure of very steeply dipping, northeast trending fractures would, in the bedrock, hopefully tend to limit its transport towards the north. And towards the east or northeast, we think the hydraulic head or the water pressure associated with the hill on the other side of the valley would create a kind of in some way blocking the movement, because the flow of water would be toward the valley. So basically, all encouraging discharge, going up through the overburden that we've observed at certain locations, with it slowly moving into the stream at a very low rate, so that under normal conditions of stream flow we don't even detect it. And we'll also be very soon having the groundwater treatment system in effect too, pulling water out of those fractures, which hopefully would prevent any further movement. So there are some good things out there, but we want to get all the wells in before we can really answer that question.
We have a lot of natural arsenic and radon in our environment. Are there any studies to show if there's any sort of synergistic effect when those combine with 1,4-dioxane? And what's the risk of the natural radon versus,
Right, well,
versus the 1,4-dioxane?
You really get to the point. First of all, there's no known interaction per se. They do cause, what radon does, different cancer. Uranium and other radionuclides can cause kidney cancer as well. But at any rate, first of all, there's no known interaction. Secondly, radon and arsenic are definite and well-known human carcinogens. There is significant contamination of well water in New Hampshire from arsenic and radon. Primarily, the issue is inhalation with radon, but well contamination can contribute to that. And so from a well testing perspective, and the state actually has an excellent private well testing website that kind of recommends what you should be doing. Private wells are very different than drinking water in Hanover because no one's testing your well unless you do, or at this point, Dartmouth is testing it for 1,4-dioxane. So it is important for well owners in New Hampshire to test their water for arsenic and radon. It can be treated, and they're very potent carcinogens, and there are human beings associated with deaths, cancer deaths associated with arsenic and radon.
As far as you know, the 1,4-dioxane were to even low and be in low levels. It doesn't seem to interact with them to make it.
There are no known interactions. But has it been studied? Not really.
Good research.
Check, check.
Okay, thank you. Jeff Wilkinson, Hanover Center, currently north of the Plume. Just had 2 quick questions. Any idea what the 1,4-dioxane was used for?
Well, I'm not positive. I know it was in the labs, but
It's used as a solvent,
Solvent,
for in the liquid scintillation fluid, which they used for research to do some counting of materials.
Okay, and my second question was there any plume or movement prior to the mitigation start process?
Sorry, prior to the, okay, you're referring to the 2000, oh, sorry. You have to turn it on. So.
Oh, you did?
Yeah, I don't know if
Okay.
that's working. But if you're referring to 2011, was there any migration before that?
Correct.
I would anticipate that there was some migration before that based on the observations that were made during the excavation. But we don't know to what extent it would be, and we do have the results of groundwater sampling right around the source area prior to 2011, which did not show the presence of 1,4-dioxane. However, there's an important caveat on that. The laboratory methods available to look for 1,4-dioxane have been improved in that time, and the method that was used initially to look for it had a detection limit which was only 50 micrograms per liter, whereas the current method that's being used is 0.25 micrograms per liter. So could it have been present there, below the 50 microgram per liter level? Possibly. The containers that were observed that likely had originally contained it were in a deteriorated condition in 2011. So it's likely it was moving at at some pace, but then potentially the cleanup work at that time could have caused an increase in the mobilization.
Or a surge? That's what I was just wondering. Okay.
Yeah.
Hi, Kim Whalen at 5 Dairy Lane. Jim, I was wondering if you could comment to us on the time frame involved in the water treatment and the amount of time it'll get that up and running, and then to actually treat and disperse the plume. I think it would settle some of our real estate anxiety. There's been many contaminated sites in every state, but a lot of owners come up with a mitigation plan, and I've seen, some come out in 1.5 to 2 years, and I've seen some still being mitigated 10 years later, trying to get them cleaned up. So if we could get a feel for the amount of time to build this water pumping facility, and actually what's going to be involved in kind of breaking up that plume or getting it out of some of the bedrock, I think it could settle us down if we knew what kind of time frame we were looking at.
Sure. Some of what you're referring to is happening right now, where we have what's called a remedial action plan that was approved by the New Hampshire Department of Environmental Services, and we're in the process of constructing a treatment system within the source area. The intent of that treatment system is to capture groundwater within the source area so that nothing moves out of there. It will also have the ability to pull some contamination back along fractures on the Rennie Farm property itself. That system, we're doing our best to get that thing started by the first of the year. So there's a lot of effort going on to complete that work. Actually, at this time, we're in the process of installing what we call groundwater extraction wells, or pumping wells, to pump the contaminated groundwater out and treat it on site. In addition to that, we are looking at the potential for doing additional remediation off-site, whether or not that would be technically feasible to do that. So some of the work that we're doing with the monitoring wells that I mentioned earlier is looking at, where's the contamination? Is there a way that we can hydraulically tap into that and extract it and treat it in a similar way to the system that we have planned and that will be starting up at the beginning of the year? Does that answer? Well, and then I think there's probably another part to that.
But that's on site. Do we know how long, or it just depends what they can pull?
Yeah, it's a little bit premature for me to give you a time frame. Once that system's started up there, it will very quickly stop further migration out of the source. Pulling back the plume will take longer, and it depends on whether it's in the fractured rock or whether it's in the soil. If we're pumping water out of the fractured rock, we'll be able to remove that much more quickly. The soils in the valley area are glacial till, and they're very, people like to call them tight. They're very low permeability soil. Water does not pass through them very readily. So it will take longer to be able to deal with that. Now, it looks like the long-term pathway for that water is to slowly discharge to the stream and then become diluted there and pass out. So there'll be, some of that will occur no matter what we're doing. There'll be a portion of that. How long the whole process is going to take to get to not detecting it throughout that area, very hard for me to say at this point. But I think getting those hydraulic controls in place will provide some measure of prevention of the plume expanding any further. It may not be expanding at this point. We may be seeing it in its full state. We don't have any data from locations where we previously had it clean and then it became dirty. But in any case, the length of time to having those in place would help. By cutting off the source, by pulling it in through the bedrock fractures, it wouldn't give it the source or the gradients in the groundwater. That is the high to low pressure sort of gradient that would cause further expansion of the plume. So that would be more rapid. Really basically getting them in place will help do that. But the long term, get it all down to non-detect, hard to put a date on that yet. Sorry for the long answer.
Hi. Seems like this 1,4-dioxane, it's in a lot of products, a lot of household products. I saw it tonight, it's in PVC piping. With regard to 668 Hanover Center, and it seems to be a heck of a mystery that it kind of shot over there, are you looking at the fact that maybe it's not related to Rennie Farm and that it's possibly, it's a slow-moving well? Is it the PVC piping there? Is it some contaminate that showed up from there that was there before?
Yeah, I mean, there was a lot of information on that slide, and I didn't go into a lot of detail, but hydraulically, it doesn't really make a lot of sense that it would be connected to the plume. And the depth of the fractures that we've seen is pretty shallow. There are plenty of other wells in the area that have wells, plenty of properties with wells that deep. Why don't we see it in any of those? So it does create a real puzzle as to how it could have potentially gotten there. At this point, Dartmouth is taking the position that it could very well be coming from the plume, and they're installing a point of entry treatment system for them, supplied the bottled water, or acting as if it came from the site. But yes, I mean, I think that is something we have to be aware of. We'll get more data in. As I said, there's some samples that were taken. They will help us understand this, because ultimately, we want to understand what the source of the 1,4-dioxane in their water is, regardless of whether or not it's the Rennie Farm property or not. But that is a real possibility.
Okay. Rebecca Sinatus with Vermont Public Radio. My question is for Dr. McClellan. You spoke quite a bit about how products have lowered their 1,4-dioxane within, consumer, and how acceptability of 1,4-dioxane. My question is, what was the impetus for that? Because, surrounding the PFOA crisis, those thresholds have been lowered too. So I'm wondering why we're seeing those thresholds lowered and what that timeline is and what the impetus around that was.
Well, basically gets down to the science associated with it. It's both the ability to detect, has gone way down, number one, and number two, the toxicology has gone forward in terms of animal toxicology, and so the risk estimates have been lowered. And as those risk estimates have been changed, that has driven kind of regulatory or even voluntary commercial behavior.
So are those evolving currently? Could this information how up to date is this information and how quickly is this information changing I'm thinking about it as the PFOA crisis happens.
Right. Well, science changes. There's no question about that. We can't say that it's static, that we may not learn more. We may learn more. Remember, we're assuming that there's actually, from a cancer perspective, no such thing as no risk. So really what we'd be talking, and from an environmental perspective, that's really the issue as opposed to occupational. So it's really this issue around cancer is the main one. And so we're assuming at the get-go that there's no risk. No such thing as zero risk. What we may find out that the slope is different. In fact, that's one of the things that changed. That is that concept of potency based on new toxicology. The slope changed, so we felt as though a lower dose would cause 1 in a million risk. But we may find out that there's actually a threshold. We may find out that below 0.25 or some number, there's no such thing as cancer as science advances.
Are you talking with people who are currently studying 1,4-dioxane? Are there current studies that are being done on it?
So the data that all of the kind of current regulations are based on risk estimates that were done, I think it's 2012 forward. So there is more work going on now.
That answers my questions, though.
Yeah, to follow up on that, on the EPA's recommendation in the rat model, can you go into a little more on the model that was done for 1,4-dioxane and the strength of that model? From what I read, they gave it a medium strength, and if you're looking at a semi-log plot of going from the rats down to humans, I could see being off by orders of magnitude, and this is possibly why they lower limits.
Well, right. I mean, so you're really getting at this issue of the uncertainty. And the uncertainty factors are not simply fudge factors. I mean, they're not simply picked out of the air. They're based on some empirical experience with certain chemicals. That they will say, if we have a model like this, if we have a human, if we have an animal, if we have a rat, if we have, blah, 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 and they'll put extra conservative.
So I'm not asking a general, I'm asking, do you have knowledge on this model for 1,4-dioxane? And if you don't, can we find out information on this, how they developed this model?
Right, I don't. I don't have that
Maybe we could
specific
look into that in the
information.
future.
Yeah, we can.
This question might have been asked before, it's for Jim, but I'm wondering, why did they choose the Rennie Farm in the first place to dump this stuff? And are there other sites that Dartmouth has chosen to dump this medical waste that we're not aware of?
Yeah, I think that might be better.
Maybe Michael has a better idea of why they chose Rennie Farm. But I can tell you that it was a licensed burial site by the state for low-level radioactive materials, which were our animal carcasses. And to my knowledge, and to all documents we've gone through, that is the only place we buried materials.
Okay. And then I guess my other question, being a dog owner, my dogs have drank out of that creek for a long time, past 4-5 years. Is there a concern there about animals?
Well, there is concern about animals. I mean, no question. And animals, like people, it would be dose, duration, et cetera, et cetera. So I think we do know something about, and you can talk about the plume and maybe some information about when the stream may have been contaminated.
Yeah, I think I could probably add to it with that kind of information. We started monitoring the stream back about this time last year, and at that point we had relatively normal levels of flow in the stream, and we were monitoring it initially on a monthly basis. After not finding anything for about 6 months, we changed that to a bi-monthly basis. And it's only been very recently that we were able to even detect anything in the stream. Again, it's likely because of the very low flow conditions that we're seeing now. So that it's not getting the dilution that would normally be occurring. So, you can just imagine that there's a reach of the stream where the groundwater is seeping out and it contains the 1,4-dioxane, and it's a relatively low rate at which it's seeping in. And normally, there's quite a bit of water flowing in through the system, which dilutes it to a point where we can't detect it. Now that's just changed, and we've seen it at 2 locations in the stream. One is just down from the location where we think the plume would be seeping up out of the groundwater and into the stream. Another one is a little bit further down, about halfway down to the confluence with Hughes Brook. So within that reach, recently we've seen it. But it's, prior to that, the data that we have, we didn't detect it there. So be very low concentrations.
Could you possibly speak to, for example, the dermatological problems that the family on Rennie Road have reported, and other health problems short of cancer that we might see manifested from exposure to the 1,4-dioxane?
Mm-hmm. Well, I can't speak directly to any individual person's health, of course. But with respect to what I've said, if you took a bottle of 1,4-dioxane, like many solvents, it can defat the skin and irritate the skin, so you could in that way. But at the levels found in the environment, as we kind of went through that whole process, the levels are nowhere close to the kind of levels that would be anticipated to cause skin problems or any organ system problems. Again, the concern or the risk, if you will, has to do with cancer as opposed to some of these other types of, whether it be skin problems or other types of health problems. And that's based on both human data and animal data.
Any other questions?
My question is for Jim. Just very simply, how many more wells have been put in since the reinvestigation of the Rennie Farm site that started back in May, I want to say? How many new wells have been put in compared to what was there before? Does that make sense?
Well, I guess the process has been ongoing. Okay. So there really hasn't been, while we do it in phases, there really hasn't been a stop to it. So we put in at this point 56 wells in total out there. And again, I think we have another 16 or 18 I had on the slide there that are planned. Now that doesn't mean that's the absolute limit. If there's a reason to put in another one, we would. But it's been a continual process, just iterative as we get in new data. It leads us to new locations for wells.
But I mean, has there been a surge in how many wells you've put in the past 6 months or so?
Yes. We put in. Initially we were working on site. It appeared that the condition was just on site. In July, I believe it was, of last year, we had detected it in the well that we've referred to as 9L at a higher concentration, which indicated off-site migration was likely. So since that time, we've installed. I don't know the exact number to tell you, but I would say it's more than half of those wells have been installed, since that time. We could count them up if
I would just be curious.
Yeah, easily more than half. Yeah.
I'm sorry, I think it was me.
We came in a bit late, and if this question was dealt with, just tell me. And maybe I should know this already, or I shouldn't be asking it, but what does the 1,4 represent?
Well, it's a chemical structure. So it's, and I can show it to you if you want.
Again, if you dealt with this already, it's fine.
No, it wasn't covered, but yeah. Yeah, it's just the positions on the ring.
There you go.
Are the red dots the 1 and the 4 or something?
Yes, right, exactly.
Yes.
So what is the 1 and what is the 4? What are they?
These are carbon, hydrogen, and actually, I don't know.
They're oxygen.
I think it's oxygen.
Yeah, they number the carbons on the ring, and the red ones are oxygens, and they number the positions. And there can be different isomers. There could be 1,3-dioxane, which would have a different oxygen structure. Very similar properties, though.
So the carbons are the 4 positions, and then hydrogens around it.
It's a relation of carbon to oxygen?
It's just the positions.
The position.
See this ring here?
Right.
It's this ring, and it's at a bond in between these different carbons on the ring.
So if you just number them, starting at the top, going around clockwise.
It's like a clock.
Yeah.
Oh, and I see inconsistencies, like here you have 1-4 instead of 1 comma. Is that dirty?
No.
Typically 1,4, but
Okay.
no, that's all it is. And there are other isomers of it, but that's the common one.
Okay.
Yeah, I have a couple of chemistry questions, I guess. So would this product have been used, is it a standalone chemical? Is it in a solution of water? Is it, how would it have been purchased and brought into the lab? In what form? And then I wonder, what is the concentration? You talk about shampoo and other consumer products, but what's the actual concentration that would have been in those products compared to what we're seeing at Rennie Road? And then third question, I guess, in shower vapor, if there's 3 micrograms per liter in water, when it turns to vapor, does that concentration stay the same? Does it increase? Does it go down?
Well, so as far as the last one is concerned, once it goes in the air, the first question is how quickly does it volatilize, meaning evaporate? And once it does that, then you're talking about it not being in the water, but being in the air, and you measure it per cubic meter. But it turns out that 1,4-dioxane tends not to volatilize well, tends to stick with the water. So it would be in aerosolized water, meaning in the tiny little droplets. And it would be presumably a pretty similar concentration. And the other question regarding consumer products, there are many, many different products that it was in, and some of these solvents that you might use or adhesives at home, some of them in industrial uses, some of them shampoos, cosmetics, so a range. They were in the consumer world. It was not put there on purpose, unlike in the laboratory or in an industrial setting. It was really a contaminant of the chemistry associated with making that product. So it wasn't put there for a purpose. They would just soon it not be there. In terms of the exact levels, They were trace. I can't actually tell you exact levels, but they were. You mentioned that it was in Tide recently. I don't know.
We don't ingest Tide regularly, though.
No, no. That's for
Some of
sure.
the
And that's right. And that most of these, these cosmetics and a lot of those are going to be less of a concern. I know the FDA. The only thing I know that I saw they think it's 10 parts per million of the packaging substance for food. So whatever that means, I don't know how much elutes out into the food itself. I don't know.
I would add, while we don't ingest it, Tide, if it goes into your leach field, it goes into the groundwater, and it's because it doesn't degrade. It doesn't get degraded in your leach field. It continues out at some concentration. So that's true for anything we put down the drain.
Right, and we just came up with some information about if you were an adult and you were swimming all summer, but you put sunscreen on before, what would your pool water measure at for 1,4-dioxane? And I believe it was 1.7 micrograms
Right.
per liter.
Per liter.
So it does have an impact, especially at the levels we're able to detect 1,4-dioxane.
How was 1,4-dioxane? Was it part of some chemical solution, or was it a 5-gallon jar of it?
Yeah, I'm not sure. I don't know if Michael knows if it was added to a solution for the liquid scintillation counter.
Yeah, in terms of how it was used at the site or how it
No,
was
in
used
the laboratory.
labs.
Yeah.
Yeah.
How did it arrive at the laboratory? Was it an isolated item, or was it part of a big chemical?
We believe it was used in the labs as a scintillation fluid, which is a counting method used in research, and then that material was brought to the site for disposal. There were some containers found during the excavation which were deteriorated or in poor condition.
But would it have been labeled as 1,4-dioxane as a product? Like ethyl alcohol or...
I don't know that the labels were intact. We don't have that detail of how it was labeled in the
So I think
60s.
that's information we need to look up, whether they mixed up the solution together and added 1,4-dioxane as the solvent, or whether it came as a scintillation fluid. I think that's what you're asking.
Right.
So we'll have to get back to you on that one.
Thank you. I'm Emily Bryant, and I lived at the Rennie Farm from 1978 to 1980. I was wondering whether you know when they brought the 1,4-dioxane up there and buried it?
Between 1966 and 1976. Okay. We really don't have a date. We didn't expect to find it, so it wasn't on our records, and so we don't have a date. Sorry.
Bob, is there any evidence that bottled water, because it's in the plastic, what's the danger or not of bottled water, just from the plastic packaging?
Right. Well, so one of the reasons the EPA is asking municipal water suppliers to start testing for 1,4-dioxane is because there's likely to be environmental. We want to find out how much drinking water is contaminated. Now, with respect to bottled water, the answer is, first of all, bottled water can come from the tap, as you may or may not know. Bottled water is all different kind of things, right? It's all kinds of different things. And in fact, famous, maybe 25 years or so ago, benzene was found in Perrier, right? It was a big scandal. Bottled water it depends upon what its source is in terms of the potential risk. Many major bottled water companies now test for a wide range of basically the EPA drinking water suite of chemicals. I don't know how many of them actually test for 1,4-dioxane. 1,4-dioxane is a level which is a chemical which the EPA says is one of emerging concern, as opposed to one which they've established a standard. So,
What I'm asking is the fact that it's bottled in plastic. The plastic itself, I've heard that if you either freeze it or if it's exposed to very high temperatures, then the toxins from the plastic go into the water.
Well, there's no question that some chemicals from plastic do leach into the water. Whether 1,4-dioxane is used in plastic water bottles, I have no idea. So possibly, I can't answer it.
Okay.
Just a quick curiosity question. So it's not naturally occurring, obviously.
Well, it's interesting. It actually is in some, like in tomato. It's in tomato. I can't tell you the level, but it's there is a trace amount in some vegetables. Trace, and I can't tell you exactly what that trace is. I think it's lower than you've been talking about, but it has to be detectable to be able to.
So if I ate 100 tomatoes a day for 5 years, that
Was there a drinking water well on the site, and was it tested?
Yes, there is a drinking water well that's still there. We were able to find that and test it, and we did not detect 1,4-dioxane in it. We also tested it for a suite of the VOCs. Other VOCs did not find that, and for radiological parameters. So, yeah.
Okay, I think we can take maybe one more question, and then we're going to have to end it because we're at past 9. Okay. Well, I thank you all for coming. I have a sign-in sheet on the table out there. For those of you who want to give me your email addresses, that would be great because I can add you to my communications email list. Otherwise, have a good night, and feel free to contact me with any of your questions and concerns. Thank you for coming.